Okay, let's start the second part of this section. And now we'll have the pleasure to hear Luigi Chierchia from the University of Rome 3 in Italy. And he is going to speak in a sequence with Gabriella Pinzari, and the title is Metric Stability of the Planetary Antibody Problem. Okay?
Thank you. Thank you very much. It's a fantastic pleasure and honor to give a little contribution to such an important event. So I want to discuss some joint work with Gabriella. The talk will be divided in two parts. I will do the first part and then Gabriella will take over. And report on some recent progress on a very old subject, which is the motion of the planets around a star assumed to be point masses. So this is the classical n-body problem, spatial n-body problem. And the main issue is to find a typical solution which stay bounded and orbiting regularly around the Sun. So the main theorem we will discuss is a theorem which was stated by Arnold when he was 26 in 1963. And in this paper, which personally I think is his best contribution to dynamical systems and celestial mechanics, and this is the statement you can find in that paper, which says that if you have, say, one body of mass 1 and n planets with masses epsilon small, and if epsilon is small enough, you can find in phase space a region of positive measure whose motion gives rise to almost co-circular and coplanar orbits around the star. Exactly what we experience in we can see in our solar system. Furthermore, this set gets dense in measure as epsilon goes to 0. And this is what takes into account the word metric in the title of the talk, which has to do with measure. So Arnold gave a complete proof, analytic complete proof in the simplest non-trivial case, which is a three-body case, one star and two planets, constrained on a plane. And then gave suggestions and hints on how to generalize this to the general case. But actually, the proof was not there, and his outline was quite controversial, and it took more than 50 years to get the complete picture. So now, this is an ancient, really ancient problem. Maybe one of the most ancient in mathematics. I will give some references before Arnold and after Arnold. And before Arnold, certainly the starting point is are the principia by Newton, which were written exactly to solve the two-body problem, to give the mathematical description of the solution, of the general solution of the two-body problem. Then there were about 200 years where people immediately realized that the three-body problem was another story. Even Newton himself, he said that was an head-aching problem. And soon they became convinced that there was no general solution, no explicit solution, and they started to look at power series expansion exactly for the planetary case. And then the problem was turned into the convergence of this series. Now, in the mid-19th century, people were convinced, eminent people like Dirichlet or Weierstrass were convinced that these series were convergent. Actually, Dirichlet had a note to Kronecker saying that he has written a proof of the conversion of the series solving the general problem, but no one found the note, and of course probably it was wrong. Then the next step was in another direction. The contribution was by Henri Poincaré, who did some major work on the three-body problem. He did not solve this problem, but went actually into the quite opposite direction, aiming that the general solution was not stable. And in occasion of this prize, which is a very interesting historic story, which I will not tell, he wrote this famous 300 pages memoir, which is considered the birth of modern dynamical system and chaos, theory of chaos. So actually, Poincaré was convinced that the series were divergent. So that was also wrong. So the problem which makes the thing difficult are the so-called small divisors, the resonances due to the conservative character of this problem. And the first to overcome this problem was Siegel in a model problem, the linearization of germs of homomorphic function. And then in the ICM of Amsterdam in 1954, Kolmogorov had this breakthrough theorem, which is the KM theorem, which he stated completely and gave a sketchy proof of it, saying that in for a non-degenerate nearly integrable Hamiltonian system, most of the structure of the integrable part is preserved, most again in a measure sense. But unfortunately, this theorem does not apply to the planetary case because of the degeneracies. So then there was the paper by Arnold, and then let me just give a few references of after him. So for 20 years about, people were convinced that Arnold settled completely the matter. If you look up in Siegel-Moser lectures on celestial mechanics, you find this statement that everything was done there. But this is not the case, and in the early 90s was Michel Herman who was the first to say that there was something missing. Then Philippe Roboutel made an extension of Arnold case to the spatial K three-body case using Jacobi reduction of the nodes. And then the first general proof appeared only in 2004, and it was due to Michel Herman, who died before that publication, and was completed by Jacques Pejos. However, they give a sort of weaker version of Arnold results, and they lose some information, and I will explain that later. They use a weaker KM. Then this is a little technical improvement in the real analytic setting of their strategy. And then the turning point was started with Gabriella's thesis, PhD thesis in 2009, and this publication here, and this is the subject which we want to talk about here. So let me start with some formula now. So the equations are very well known. So you take Ui is just the position in a physical three-dimensional space of a body with the index I. I runs from 0 to n. 0 will be the label of the sun, and 1 to n the planets. So these are just Newton's equation. You can see there. And this is a natural system, so it has a natural standard Hamiltonian associated to it, which is written over there. It has a kinetic part and a potential Keplerian part. And this symplectic form is the standard one, standard symplectic equation, where capital Ui are just the linear momenta, the velocities. Now, the Keplerian, what makes this problem particularly difficult is that the problem has a lot of structure and symmetries, which actually are a hindrance to non-generic features. In particular, the system has 7 integral of motion, so 6 more than the energy itself. And this is due to, of course, translation invariance and rotation invariance. And the integrals are the vector, total linear momentum, and the angular momentum. Now, you can do, so when you have extra integrals, there is a general procedure to make symplectic reduction. However, to do it explicitly is very hard because you have to find explicit variable, global variables. So, but this calls for what is called symplectic reduction. So if you look at the manifold, that symplectic submanifold of total linear momentum 0 and total center of mass 0, this is invariant and reflects all the motions. So you can study the general motion just by looking at this symplectic submanifold. And Poincaré showed how to make the symplectic reduction. So this is done simply by this heliocentric coordinates xi equal ui minus u0, so the relative position of a planet with respect to the plane. Then you rescale the masses, m0 as order 1, but the other one are order mu, small. And then the original Hamiltonian gets transformed into this form here. Into this form here, and then you have a couple of features which comes nice. First of all, you see that now the indices start from 1 here and there, so this means that the position and it has 3 degrees less of 3 degrees of freedom less. No, you lowered the dimension. Little x0 and capital X0 are not explicitly there. Okay, so this is an important remark. The second, of course, is that it brings the nearly integrable structure very neatly, and then this term here is just the sum of n decoupled two-body problems. The two-body problems of the star with one single planet. This problem is integrable, and you can use Delaunay variables to make it clear. But notice that this system here is at 3 degrees of freedom. These are vectors in three-dimensional space, while when you integrated, only one actual variables appear. So this is quite degenerate. This is part of the problem. So, and then there is another problem with Delaunay coordinates, which is that they become singular exactly in the planetary case, exactly in co-planar and co-circular motion they become singular. So this was, of course, very well known, and the standard symplectic variables that you use are the Poincaré coordinates. In these Poincaré coordinates, which are n action angle variables, 2n action angle variables, and 4n Cartesian variables, the system takes this form, where you have the Keplerian particles, the perturbation. So you see capital lambda are the action variables, but are n, and then you have these lambdas which are related to the mean anomalies that describe the position of the planets around the sun. And then you have these 4n Cartesian variables. Now, the Cartesian variables have the origin exactly in the co-circular and coplanar motions, and you can see, so little l, little lambda is a fast variable, it's a fast angle. So this, of course, calls for averaging theory. So you have to look at the average of the perturbation to have some hint about the dynamics of this problem. And if you do the averaging, and after the rotation of the quadratic part, first of all, it's an even function of the rectangular variable, and then you see immediately that it has an elliptic equilibrium around the motion we are interested in. So if you truncate now the averaged part, you have an integrable Hamiltonian, because it's the sum of this part which is integrable and these which are harmonic oscillators. And the dynamics is, the truncated secular dynamics is it was here. The little lambdas run around this n-dimensional tori, and the eta, the xi eta and qp just rotate on these circles harmonically. And the product of this is a 3n, so n dimension here and 3 and 2n dimension here, which makes a 3n invariant torus, Lagrangian torus for the system. And the truncated dynamic is foliated by this tori. And the problem is to see how this is maintained in the general problem. So the natural action angle variables for this system, of course, are the lambda, capital lambda, little lambda, and the polar action angle variables for the harmonic oscillators. So in the 63 paper, Arnold formulated a generalization of KM theory in a general setting, and he called that the fundamental theorem, which is a really deep extension of Kolmogorov theorem. It's a general theorem which deals with Hamiltonian of this kind, so the same kind of the n-body problem, lambda lambda, and then Cartesian variables. Okay? So, and assume that the average of f has exactly the same structure. You see, this is the Birkhoff normal form of order 1, and these are the Birkhoff invariant of first order. Exactly as before. Now the hypotheses are, first one is the hypothesis that you find in Kolmogorov, basically, that this map lambda to h prime to the gradient of lambda, which is a map from Rn to Rn, is a local diffeomorphism. But then you have to have also hypothesis on the average, otherwise it's clear that you could get also no tori at all. So the assumption are that the singular frequencies omega j are non-resonant up to order 4, so that you can put the system into Birkhoff normal form up to order 2. So this is R is, again, Rj is this quantity here, and tau is an m times m matrix, okay, the quadratic part. And the assumption is that this matrix tau is invertible. And this is the twist assumption, the analogous for the secular variable of this assumption. Okay, and then the thesis is that for mu small enough, you can construct positive measure Kolmogorov set, which are Lagrangian, Diophantine invariant with not the general normal form. You have explicit, you can find explicit measure estimate and so on. Now the problem is that this setting applies to the planar case, and Arnold checked the case of 2 planets, but not to the spatial case because of other degeneracies. And let me tell you what these are. So the secular degeneracies are that the Birkhoff invariants satisfy this R resonant, actually, R resonant. And they satisfy this thing, one of them, the last one, say, and these are all related to the vertical modes, not to the planar one. So it's really a feature of the spatial problem. This was known to Arnold, but this was not known to him. And this is also a problem, and was discovered, it's called Hermann resonances, because it seems that he was the first to pointing out in such a clear way. But then there is another thing, is that if you want to check this torsion, admitting that you can write down, calculate, you have to do 4th order calculation, which are pretty hard. And Hermann tried, and in simple example, he realized that the matrix tau was could be 0, could be degenerate, could have determinant 0. And this is in fact was not known to him, but it was proved by Gabriella and myself later. And this is a major problem because there is actually no torsion there. So the strategy that Hermann and also Rusman separately followed is to weaken the KM theory losing some information, but with less hypothesis, and they need only to check to have this part explicitly. And then the assumption are that, again, as before, the Kolmogorov assumption, but then it's enough to assume that these frequencies here are non-planar, which means that they're not identically contained in some hyperplane. Under this hypothesis, you find again positive measure set of Lagrangian tori, but no Kolmogorov normal forms, and also no explicit measure estimates. So how am I doing it? But the problem is that in the spatial case, this map here actually lies in the intersection of two hyperplanes. So you cannot apply even the weak KM, which is not the weak KM theory which Aug14Thu will speak about. This is, so to speak, it's classical weak KM. So the strategy that they followed, Michel Marcos followed, was very ingenious, and so they introduced extra variables and modified the Hamiltonian H with a fictitious Hamiltonian, something not physical, but in such a way that this function here now satisfies the hypothesis, and you modify it in a way that H sub rho commutes, Poisson commutes with the original one. And this can be done explicitly, because you see this quadratic part is just a vertical component of the total angular momentum. So it's a preserved quantity. And then you apply the Hermann-Hussmann theory to this, to the fictitious Hamiltonian, and then by some general abstract Lagrangian intersection theory, which says that H and H rho have the same Lagrangian transitive tori, you can say that you have tori also for the original system. But you lose information also on you don't know that they are diaphantic, for example. So our strategy instead is, in a sense, more old-fashioned, and I will just very synthetically say what it's about, and then turn the word to Gabriella, who will give more geometric insight on this strategy. And the idea is to introduce new symplectic variables, which extends Jacobi's reduction to the general n-dimensional case, and to look at a partial reduction of rotations. So to lower still by 2 degrees of freedom the phase space, and on this reduced phase space, check actually that the torsion is different from zero, which is a very hard computation. It's a fourth order computation, and the bottom line is that the torsion is there if you look at it in the right variables, and this, and then we can apply essentially Arnold's original fundamental theorem, or a slight elaboration of it, but which managed to complete Arnold project on this subject, and then maybe this is a good time to switch.
Thank you very much. Now, in complement, we have Gabriella Pinzari, as you have mentioned several times. And she's from Universita Federico II, Napoli. Please.
Thank you very much. It's a great honor for me to be here. And I shall start talking. I shall start talking of a procedure that was mentioned by Luigi, that is a classical procedure of complete reduction of the nodes by a complete reduction of the number of degrees of freedom in the case of the three-body problems. This procedure was developed, is very classical and was developed in the 19th century by Jacobi and next to Rado. It was mentioned in the paper by Arnold that should be used to prove his theorem in the case of the spatial frequency problem, and in fact, as also Luigi said, it was used by Philippe Robutel to prove his theorem for that case. We have two planets that move, two planets and a sun that move in the space. The system is governed by a system of differential equation of the order 18, because we have 3 coordinates for each particle and 3 particles, and the second order differential equation for each coordinate. But since the motion of the center of mass of this system is known, we can suddenly reduce through the heliocentric reduction that Luigi mentioned to study the motion of a 6 degrees of freedom system, that is the system of the 2 planets referred to a fixed star. Then we can further reduce the number of degrees of freedom using the invariance by rotation of the system, simply fixing, in a sense, the motion of the line of the nodes. This is what follows. The reduction is not defined when the motion are coplanar, when the motion of the 2 planets belong to the same plane. But if they do not belong to the same plane, we consider the 2 planes are determined by the position and the velocities of the 2 planets. Such 2 planes intersect along a line that is usually called the line of the nodes, and this line moves. However, in this picture, there is something that does not move, and this is the total angular momentum of the system. C, this is the sum of the 2 angular momenta of the 2 planets. The total angular momentum and the line of the nodes are orthogonal one to the other, so if we imagine a system of a reference frame that has its third axis in the direction of C and the first axis in the direction of the line of the nodes, this system rotates. Here we have the plane of one of the orbits of the 2 planets, and we have represented on this plane a system of symplectic polar coordinates that are referred to the line of the nodes for each planet. Those are coordinates that are denoted with R and phi, capital and small letters. The small r and phi are position coordinates, and they are polar coordinates of the position, bar x, on the plane, while the capital R and capital phi are related to the composition of the conjugated momenta with respect to the radial direction and the tangential direction, as it is as in this picture. And in particular, the quantities capital phi here are just the lengths of the angular momenta of the planet. Here we have the plane, each plane of the orbit, and the invariable plane. The invariable plane is the plane that is perpendicular to the total angular momentum, while the orbital plane is perpendicular to the angular momentum of the planet. The inclinations among such 2 planes is uniquely determined by the triangle of the 3 angular momenta, by the Euclidean lengths, by the sides of this triangle, phi 1, phi 2, and g. Phi 1 and phi 2 would be the Euclidean lengths of the 2 angular momenta of the planet, and g, the Euclidean length of the total angular momentum. So, using very easy geometric relations, we have that the coordinates of each planet with respect to the rotating frame, the frame that has its horizontal plane along the variable frame and rotates with the line within the line of the nodes. These coordinates can be very easily, in an elementary way, found by using only geometric arguments. And the result by Jacobi and Rado is that if we substitute the coordinates relatively to this rotating frame into the Hamiltonian, the Hamiltonian equations are preserved for the 8 coordinates, for the 8 polar coordinates of the 2 planets. So we have completely reduced the number of degrees of freedom of the system to 4, and g, the Euclidean length of the total angular momentum, the equation appears just as an external fixed parameter. So the result is not trivial because, as I said, the reference frame rotates. Arnold knows very well that, unfortunately, in the case of more than 2 planets, that more than 3 bodies, there is that this method works for 3 bodies, but there is not a similar one in the case of more than 3 bodies. And so, in his paper, he suggests a quite somewhat different procedure to treat the case of more than 3 bodies. He believes that it is possible to find just a sort of partial reduction of the invariance of rotation by rotations of the system in order to determine a new system of canonical coordinates that has such that in the system there appear 2 functions, chi1 and chi2, that can be constructed using the component of the total angular momentum, such that their Poisson parenthesis is equal to 1. And in this way, he believes that it is possible to overcome the problem of the identically vanishing eigenvalue. 40 years later, Frank Malige, Philippe Robutel, and Jacques Lascar construct explicitly this system of coordinates in the case of 3 bodies, this is with two planets. And for this construction, they just start from the reduction by Jacobi and Rado. For the general case, they propose a formal algorithm, about in the midway between the papers by Arnold and Malige, Lascar and Robutel, and exactly in 1983. Debris discovered a set of canonical coordinates, psi, r, and phi, capital and small letters, that are good for general system of n particles, that in the case that n is equal to 2, so for the 3-body problem, adjust the coordinate of Jacobi and Rado. Such coordinates remained unnoticed for many years, and as far as I know, they were used only in the 90s by some Spanish researchers, Zalcar and Ferrer, just in the case of the 3-body problem, in which case they were already known since Jacobi and Rado. And Andrea Debris himself believed that maybe because of a certain hierarchical structure that I should try to explain, they would be unuseful and never used by then. And in fact, they were never applied to the n-body problem until they were rediscovered much year later by us. So the major role of the coordinates by Debris are the psi coordinates. Those are vertical coordinates, and above all, among these coordinates, the 2 last couples, the 2 z's and the 2 g's. Those last pairs, since they have a spatial meaning, are denoted with such different symbols, z and g's. Capital and small letters, capital letters for actions, small letters for angles. The importance of such 4 variables is that among them there are 3, the 2 z's and g, that disappear from the Hamiltonian. They are cyclic. So they reduce the number of degrees of freedom by 2 units. 2 units are not 3 because there is a conjugated couple, the 2 z's, that reduces the number of degrees of freedom only 1 unit and not 2. The importance of the fact that there is a conjugated couple, the couple of the 2 z's that disappears from the Hamiltonian, is at the origin of a strong degeneracy in the system that prevents the direct application both of the chaos theory developed by Arnold in his paper of '63, and also of the weaker theory of which Luigi talked, developed by Harman and Russman later. And this degeneracy is such that if we try to compute the Birkhoff normal form associated to the secular system, then we find an infinite number of degeneracies. An infinite number of coefficients in this Birkhoff normal form vanishes, and so it is impossible to apply any chaos theory to the system. The basic objects of the reduction by Debris are these ones: the angular momenta of the planet, the total angular, that are denoted with psi j, the total angular momentum, C of the system, and the so-called partial angular momenta, the Sj, the sums from 1 to j of the angular momenta of the planet. And a basic structure of this reduction is this tree. This is a tree of frame that starts with our initial frame, F0, this is arbitrary, and ends with any of the frames of the orbit, F1 up to Fn. So, to reach any of these orbital frames starting from S0, one has to do a walk along this tree, and so to make a sequence of rotation, passing also through some other frames that are denoted with F with this star, that have their third axis just in the direction of the partial angular momenta. And these are precisely those frames that are prejudged to be not physical and to cause this hierarchical structure we talked about. In this picture, there are represented the two variables, capital Z and small z. We have our initial frame, I, j, and k, the total angular momentum, and the planet through the total angular momentum and the vertical axis. The variable capital Z is just the third component of the total angular momentum, while the angle Z is the longitude of the line nu n, that is the line that is perpendicular to the plane of CLZ, or equivalently, this line is the intersections of the two planes perpendicular to C and Z. These two variables are two integrals because C does not move, and the rotation that overlaps our initial system to the system that has as a third axis the total angular momentum, and as a first axis just the line un of the previous picture, this rotation is completely negligible, and so we can just study the system starting from this frame that is the invariable frame. Here we construct a triangle determined by the latter of the angular momenta, Cn, and the sum of the first n minus 1 angular momenta and the total angular momentum Sn. In the case that the planets are two, this triangle, this construction just reduces to the construction by Jacobi and Rado. Here we have that the angle G is the longitude of the line nu n minus 1 that is perpendicular to Sn minus 1 and to this n. This angle moves because the triangle moves, but however it is cyclic because it is conjugated to capital G, that is the Euclidean length of the total angular momentum. In the case of free bodies, the line nu n minus 1 is just the line of the nodes. However, if the number of planets is more than 2, we can iterate this procedure. And so we will have other variables, the psi j, that are the lengths of the partial angular momenta, and other angles, the small psi j, that are longitudes of other node lines. The construction ends until we'll reach some orbital frame that will say the number j plus 1, and on the horizontal plane of this frame, we establish a system of polar symplectic coordinates, as we have seen in the case of the reduction by Jacobi and Rado. But in order to deal with the application to the planetary case, we have to switch from this horizontal variables, the two r's and the two p's, with the two new variables that are, however, very classical, that are called the planar Delaunay variables, and those are related to the elements of the Keplerian ellipses that can be constructed starting with the polar symplectic variables. In particular, the angle small gamma would be the longitudes of the perihelia of the ellipses, while the angles L would be proportional to the area spanned on this ellipse by the planets. The variables capital G are just the same as the phi, the Euclidean length of the total angular momentum, while the variables capital lambda are not represented here. They are just the square roots of the semi-major axes of the ellipse. So the idea is now to use these new variables, the lambda, the g, and the psi's, and their conjugated angles, in order of, in substitution of the classical spatial Delaunay coordinates that were classically widely used into the iterator as in application to planetary series. And this is a reminder of what are the classical spatial Delaunay coordinates. Those are coordinates that are planar Delaunay coordinates on plane, while the directions of the plane of the orbits that are determined by the two variables, capital theta and small theta, are just determined with respect to the initial frame I, j, and k, and not to the invariable frame, as in the case of the planetary, of the modified the variable by debris, and they do not reduce at all. The number of degrees of freedom. So, in order to deal with the case of the singularities of the maps by debris and of the planar Delaunay map, we introduced new variables that are regularized variables. Those are different from the variables by debris in two respects. At first, because they reduce the number of degrees of freedom by just 1 unit and not 2, because since we wanted to regularize all the singularities, this is due to the fact that we want to regularize all the singularities. And the other difference is that they are not in form of action, angle, or coordinates. Part of them, the two lambdas and L, are action and angles, while the other variables, the eta, the c, and the p, and the q, are rectangular variables. In particular, there are two variables, Pn and Qn, that are integrals in the system, that are defined only in terms of integrals. So they both disappear from the Hamiltonian, and here they play the role of the two z variables, of the coordinates by debris. So just for comparison, we want to compare them with the classical Poincare variables that have, which Luigi talked, that have a very similar structure, but they do not contain a cyclic couple. And here is the conclusion of the story. The planetary Hamiltonian is considered in this new set of regularized variables. The system has 3n-1 degrees of freedom. However, it has an extra integral, the Euclidean length of the angular momentum, that has this nice expression. This extra integral introduces a symmetry into the system. The zero of the p and the q is again, as in the case of the plan of the Poincare variables, an elliptic equilibrium point for the cellular system. Its first order Birkhoff invariant with respect to this equilibrium point that are n plus n-1 to n-1 are the same as in Poincare variable, except for the identically vanishing one. So the degeneracy due to rotations that was known to Arnold, as Luigi said, here disappears. And the system exhibits only Hermann's resonance. And we explicitly computed this first order Birkhoff invariant, and we verified that they verify just only Hermann resonance. However, this resonance is not an obstacle for the construction of the Birkhoff normal form, just because of the symmetry that is introduced by the integral g, and we computed with some effort the torsion of the system, and the result, it verified, does not vanish. I would conclude with this conjecture by Arnold, who in 1963 thought just that. It was, as I mentioned before, it was possible to construct two functions, chi1 and chi2, that have the same form of the Poincare variables, such that chi1 and chi2 are one of the variables corresponding to the inclinations, the p and the q, and the system is reduced to 300 degrees of freedom. He thought that should solve the problem. And I finish here. Thank you very much.
Thank you very much, Gabriella. Absolutely precise on time. Now, do you want or you allow either both or one of you to have questions from the audience? couple of questions. Is it okay if I?
Of course.
So please, the floor is open. Yes?
At this moment, the problem.
I do, wait, maybe he'll bring a microphone.
So, is it true that at the moment the problem originally stated by Arnold is fully resolved to them?
We think so.
So, I'm going to continue with some stuff.
You have to speak louder, please.
Is there a clear direction of continuation of this, or it's kind of finished now?
I mean, Arnold project in this sense is completely finished. There are still some, of course, open connected questions, very interesting. For example, this thermal resonance is still not understood. The real origin of that resonance, even though it's not a technical problem, still is something to be understood. Then there might be, of course, more problem about the stability, like the Goroshev type, things like that. But we believe that Arnold's original idea and project is completely finished.
Okay, let's thank the speakers.